Hi everyone, thanks for checking out my video. Today we're going to get into the weeds a bit with blacklights and glow-in-the-dark stuff. And we're going to cover a bunch of topics to that end. We're going to talk about the spectrum, both the visible and invisible, the difference between common blacklights and true blacklights, the color white and its relationship with blacklights, and then finally luminescence, fluorescence, and phosphorescence. What is the difference between all those? As we get started, I want to be honest with you all. If you're not really into sciencey stuff, this first video is going to be a bit dry. We're going to talk about, in very broad terms, the physics of how blacklights make things glow. And there's some foundational knowledge we all need to share going into this before I get into the fun stuff you actually all care about. This will probably end up being around 20 or 25 minutes, but I'll try and make it as interesting as I can with real-life examples, demonstrations, and spectrometer reports I took for the purpose of this video. Stick with me and you'll come out the other side being able to articulate not just what blacklight is and isn't, but exactly how it works. And also, hopefully, better able to make practical decisions on what to purchase for any glow-in-the-dark setup you're creating. Alright, let's start with defining the spectrum. But more specifically, since the spectrum covers everything from deadly cosmic and gamma waves to radio waves, we're talking about the visible and invisible spectrum of light. The spectrum of light is how we describe the form of energy that we see with our eyes. This energy is an electromagnetic wave, and we measure the length of these waves in nanometers. The important part to remember from this first bit is this measuring in nanometers. That's how we're going to be quantifying the light we look at. The visible spectrum exists from roughly 400 nanometers to 750 nanometers. Within that range, our eyes are particularly sensitive to light at 555 nanometers in daylight, sort of like a lime yellowish green, and 507 nanometers at night, a basic bright green. So we already have some practical information. All other factors being equal, at night or under typical blacklight conditions, the color most people will see the best is a nice bold green. Ultraviolet, or UV, is the next lower category of waves and starts the invisible part of the spectrum. Most of the spectrum is invisible, in fact. The visible spectrum takes up only a small fraction of the whole. UV has a shorter wavelength, all the way down to 100 nanometers. UV is further categorized into three types: UVA, UVB, and UVC. We care mostly about UVA, the next door neighbor to the visible spectrum, approximately 400 nanometers down to 315 nanometers. Below that is UVB, and below that is UVC. As wavelengths get shorter, the energy it contains increases. This is the key to why things glow, so I'll say that again. As wavelengths get shorter, that is, as the number in nanometers gets smaller, the energy of the wave increases. Let's take sunlight as an example. Sunlight contains energy as both visible light and ultraviolet light, in addition to other energy that isn't relevant to this discussion. We'll arbitrarily consider the visible spectrum the baseline amount of energy for light for our purposes today. So everything below that gets more and more energetic. The light or wavelength that lets us see the color green has more energy than the light that lets us see red. Green has a shorter wavelength. Purple light has more energy than both green or red light. Its wavelength is shorter than both of them. UVA has more energy than any color in the visible spectrum. It's mostly harmless, but you still shouldn't stare at a blacklight for extended periods of time. UVB has more energy than UVA. It's what causes sunburns. UVB bulbs are what they have in tanning beds, and if you've ever used one, you know that they come with a load of warnings and require the use of tinted goggles. Because you can't see ultraviolet light, you don't know to close your eyes when looking at it, leading to severe retina damage in a short time if you aren't using eye protection. UVC has even more energy than UVB, is highly energetic and dangerous, and exists just prior to X-rays on the electromagnetic spectrum. UVC is used in ultraviolet purifiers because it can destroy the DNA within cells. Thankfully, Nearly all of these higher energy waves from the sun, like UVC and most of UVB, gets filtered by our atmosphere before it ever reaches us. One last important thing to remember is that there is no hard line between the visible and invisible parts of the spectrum. We tend to think of visible and invisible as existing in separate conceptual boxes. Light is either visible or invisible. And it's a little weird to talk about invisible light in the first place. That's fine when you're talking about something your eyes can or can't see. But when we talk about energy, which is something much more ambiguous, that thinking will trip you up as we talk about this more. Even the distinction of UVA, UVB, and UVC are just arbitrary lines we've drawn based generally around points of which those energies begin to have different effects on us. The difference between invisible UV and visible purple is as small as the difference between visible orange and visible red. Remember, the spectrum is just that, an unbroken continuum from unfathomably short waves to nearly as ridiculously long waves. Just like regular lights, black lights give off a range of light, which tends to peak at a certain wavelength. This peak is the number they're usually advertised at, if manufacturers disclose the number at all. Because this is the peak wavelength, and because they are not perfectly efficient, they also produce energy on both sides of the peak. They produce some light even further into the UV spectrum, and some light that bleeds or leaks into the visible range. The purple light we commonly associate with black lights is the bleed over or waste light into the visible spectrum. By waste, I mean specifically in the context of generating UV light. It can still be useful in other contexts. I've taken 2 of my own Amazon-bought generic black lights and tested them with a spectrometer. Both of them are in a standard floodlight form. This one is 30 watts, and this one is a whopping 150 watts. Let's take a look at those spectrometer results. Commonly available blacklights produce a peak wavelength of 395 to 400 nanometers. Remember, the visible spectrum starts around 400 nanometers. You can see that this one peaks at almost exactly 400 nanometers. My meter actually read 399. That means roughly half of the energy produced stays in the UV range, while half of the energy is wasted as visible purplish bluish light. The 150 watt light has a nearly identical result. It's putting out the exact same wavelengths of light, just more of it. These results are so similar, I'm tempted to crack them open and see if the individual LEDs are the same. These are different brands, but parts for items like these are frequently purchased cheaply through a Chinese manufacturer, then assembled into a housing elsewhere and given a generic brand name. Amazon is absolutely rampant with these type of products. I wonder if both of these brands use the same LEDs, just housed and arranged differently. So this purplish blue light is no different than any other blue or purple light from regular non-black light sources. Some of you may have seen videos where people purport to hack their iPhone flashlight into a black light by covering it with tape and coloring it using purple and blue Sharpies. I hope everyone realizes that this is obviously not a black light. It sounds ridiculous right out of the gate, but maybe we don't know exactly why it's ridiculous. After all, highlighters still seem to glow with it. I thought it'd be fun to reproduce that hack, take a look at it under a spectrometer, and explain both why it seems to work and why it's not really doing what they claim it's doing. 395 or 400 nanometer blacklights are very cheap to make. And though not incredibly efficient, they do produce some UV light. They work fine for most purposes because most people have just gotten used to the purple light. After all, old filament-style non-blacklight bulbs were wildly, nonsensically inefficient. Nearly 98% of their energy was wasted as heat, but we still got by over a century with them just fine. Anyone else have parents who would flip out when you didn't turn the lights off after leaving a room, or Maybe you still have that habit today. I know I do. Imagine your parents getting upset over it, let's, say in the car after leaving the house, and you responded with, well, Father, 98% of that money we're wasting is basically just going towards inefficiently heating the house anyways. I would have been yeeted from the vehicle before I finished that sentence. So, regular blacklights aren't great. But then, what other option is there? Well, there are a category of blacklights called true blacklights. These produce a peak wavelength of around 365 nanometers, much further into the UVA spectrum. Because the peak is further into the UV spectrum, the off-peak energy stays in the UV range far more than common blacklights. More than 99% of the energy these produce stays in the UV range. And I should clarify something about this picture. My spectrometer is not made to read below 380 nanometers. So the peak here is just the meter's way of saying, of the light I can see, the most powerful wavelength is 380. According to the manufacturer's specs, which I believe, because by all accounts they're a reputable brand, this light does indeed peak at 365. I'll switch to their spectrograph now. Notice how their spectrograph report trails off around 380, but my meter shows a drop of light pushing past that 400 mark. That's because of how my vertical axis was calibrated. The light my meter could detect was minuscule compared to what it couldn't detect. Also, that area between 380 and 400 is kind of a gray area as far as invisible and visible. We're using 400 as a standard, but shorter wavelengths are visible to some people. A small amount of light does leak into the visible spectrum, which we see as a light bluish color. Much different than the usual purple, or at least I see a big difference. I think once you see a true blacklight, it's fairly easy to tell the difference between them at a glance. Because less light is generated in the visible spectrum, the non-glowing surrounding area won't be as well lit. So, not only is the true blacklight imparting more energy to your glowing materials, the contrast between your background and your glowing stuff is greater, further enhancing their apparent brightness. The visible light looks dim, but it's still quite perceptible. It's important not to judge the light by what you see. What you're seeing is less than 1% of the total energy being put out. If you have a 30-watt common blacklight, but half of that power is being used to generate visible light, compared to a true blacklight that has typically less wattage but generates far more UV energy from it, which is the better buy? And talking about which is the better buy, my final point about choosing blacklights. Yes, true blacklights are much better than common blacklights at making things glow, but sometimes that's not the only consideration. Cost is almost certainly a factor, right? 365 nanometer LEDs are significantly more expensive to make, which is why you'll pay a premium for true blacklights with less wattage compared to common blacklights. You have to decide if that premium is worth the glow, which, while obviously better in carefully controlled settings like this, will your audience notice it? Also, maybe some people want that purple glow in their scene. Common blacklights will illuminate not just the blacklight reactive stuff, but much of the surrounding scenery too, because of the visible light leakage. Even if everything around the glow is painted black, remember that no black is perfectly non-reflective, though I've seen some stuff getting close. So you're always going to get some reflection from that purple light. If you're counting on that light to help people see where they're going and not walk into walls, maybe staying with the cheap 400 nanometer blacklight is the way to go. True blacklights will illuminate far less of their non-reactive surroundings, and if the area they're in is otherwise dark enough, you might need to consider adding more pathfinding signage or something so people don't trip and knock stuff over. Actually, before we move on, let's take a look at one more blacklight. This is an old incandescent blacklight. Literally, this bulb is at least 20 years old. It's not a CFL or LED in incandescent bulb form. It has a filament in it, At first glance, this looks very blacklightish. There's a purplish light, but white things don't really look bright. Even this highlighter seems to be struggling to glow. This is not a blacklight. And I'll level with you all. I largely knew what these spectrometer graphs were going to show before I took the measurements. I didn't know precisely what the wavelengths these specific blacklights were putting out, or the spread from the peak wavelength. And if I wanted to authoritatively talk about this stuff, I wanted to put in the effort to get accurate data. This bulb was the only one I measured that caught me off guard. I was positive this would be a pure purple light, peaking somewhere around 410, 415, with no UV at all. I'll think you'll all be surprised as I was. I even recalibrated my meter and took another reading because I didn't believe the first one. It's not even purple. It's magenta, with a bit of blue and a dash of green and orange. It's so magenta that it did the opposite of the true blacklight and topped out my meter. It won't read past 780, so the peak could be even higher. I had to rescale my y-axis on this even to see the blue and other colors. So not only is this not giving off any UV, it's more akin to a sun lamp than a blacklight. Hopefully you can see, but even the highlighters are having trouble glowing. Their glow is inhibited by the overwhelming long wavelength of light, and almost complete absence of shortwave light. Now that we have a general understanding of the spectrum and blacklights, I want to talk about the color white and its relationship with blacklights. The color white, in and of itself, is no more blacklight reactive than any other visible color. White is, after all, just the reflection of all visible colors. However, there are two qualities that makes considering its use worthwhile when using a blacklight. White is the most reflective color. By definition, it reflects all the colors of the visible spectrum. This includes that visible waste purple light and any glowing fluorescent light. So, in an otherwise dark room, white will show up under most blacklights, if for no other reason than it's just reflecting the non-UV visible light really well. If the white itself doesn't have any blacklight reflective properties, it will be dimmer under a true blacklight because those put out less visible light to reflect. But finding a non-blacklight reactive white to test this on is trickier than it sounds. Because we humans like our whites white, bright white. We like our whites so bright that manufacturers of paper, paint, textiles, and cleaning chemicals regularly add a touch of fluorescence to their white products or chemicals, like detergent. So a white shirt that is blazingly glowing under blacklight not only has the previously mentioned reflectivity working in its favor, but a considerable amount of UV reactive fluorescence in it as well. More so if it was recently washed. In daylight, we obviously don't see these whites literally glowing, but we do say things like, wow, that white is bright, or that's a really white white. That's fluorescence, tricking our brain into perceiving something as brighter. Now that I've set a foundation with a quick background on energy, colors, and UV, let's start talking about that fun stuff like fluorescence I just mentioned. Finally, right? What makes something glow under blacklight? There are three terms I want to talk about: luminescence, fluorescence, and phosphorescence. These are the terms you're going to see when shopping for UV reactive products like paint. Luminescence is the overall term for something that produces light without the use of heat. Chemiluminescence is one we're all familiar with. There are chemicals in glow sticks that mix when you break them. Those chemicals react to produce light. Bioluminescence, which is when animals use chemicals to produce light, is a subtype of this too. LEDs produce light through electroluminescence. Old school light bulbs would not be luminescent because their light is produced by using electricity to heat a filament. Fluorescence is when a material absorbs one form of highly energized light, like UV, and produces a less energized light, like visible light. This is the effect we all recognize as glow. Energy is expended in the process, so you need a shorter wavelength or more energetic light to convert to a longer wavelength light. Looking at a spectrograph, fluorescence only works from left to right. You can't make things fluoresce with infrared light because IR already has less energy than visible light. So any expenditure of energy would create a longer wave even further away from visible light. Now, before anyone calls me out saying there are processes to create shorter wavelengths from longer ones, yes, but that's not fluorescence, and it's beyond the scope of this video. With fluorescence, this glow is only maintained as long as it's provided energy, like UV light. When the light is removed, the effect stops nearly instantaneously. The term phosphorescence is often used interchangeably with fluorescence, but there is an important difference, especially for the audience I'm targeting this video at. A phosphorescent material creates glow in essentially the same way as fluorescent materials. It takes in higher energy light, which could be UV or even the more energetic colors of the visible spectrum, and kicks back a lower energy light, the visible glow. However, phosphorescent materials can take in and store energy. Again, the deep physics of it are beyond the scope of this video, but it's really cool stuff with high energy orbits, forbidden mechanisms, and other fun atomic phenomena. Essentially, that energy can only be depleted at a certain rate. It's constrained in its ability to rid itself of that stored energy. So it continues to produce glow for seconds, minutes, even hours after the UV light is taken away. This slow, constrained conversion into visible glow also means that this effect is often not as bright as fluorescent materials. So, to sum up, luminescence means anything that produces light without using heat. Fluorescence is any material that glows but stops as soon as the light is taken away. Phosphorescence is any material that continues to glow after the light is taken away. And fluorescent material tends to glow brighter because the conversion to visible light is relatively unrestrained. It's able to dump all of its energy out immediately as a bright glow. Phosphorescent material continues to glow after the light source is taken away, but tends to glow dimmer because of fancy physics reasons. Of course, quality and the specific type of material matters. A cheap fluorescent material might not glow as brightly as a quality phosphorescent one. Now, as promised, I'm going to reproduce the hack your phone's flashlight into a blacklight trick. The idea is that by taking a piece of clear tape, putting it over your phone's light, and then coloring it purple and blue, you create a blacklight. I hope everyone watching this realizes that this isn't how any of this works. The trick relies on people not realizing that the purple light a blacklight leaks isn't what makes things glow. Of course, we're almost 20 minutes wiser now, and you all know this, if you didn't before. You can't make UV by subtraction. That is, by taking regular visible light and using a purple and blue marker to filter out all the visible color past purple. It doesn't create UV that wasn't there before. Just like with the incandescent blacklight I tried earlier, it's just purple and blue. Plain blurple light. Here's the spectrograph of my iPhone's flashlight with no filter. Lots of blue, and lots of the colors our eyes are good at seeing. And now here's the graph of the light with the blue-blue-purple filter on it. The blue region hasn't budged, but everything else is essentially filtered out. Ironically, it even filtered out what little light started to creep into the UV range. My phone was a better UV light with no filter at all. But then they show highlighters glowing under it. What sorcery is this? Well, that sorcery is fluorescence, the exact same effect we just talked about, and a bit of an ambient light trick. The thing is, the specific chemicals in highlighters don't require UV to glow, though it helps. They look bright even in indoor incandescent light, right? Well, those bulbs don't put out UV at all. That's what makes them highlighters. The ink looks unnaturally bright. If you remember what I said about how fluorescence works, it takes a higher energy, shorter wavelength, and converts it into a lower energy, longer wavelength. UV certainly qualifies as higher energy for any color in the visible spectrum, and let's take a yellow highlighter for example. What would be a shorter wavelength than yellow? Well, pretty much any other color in the visible spectrum. Green light, blue light, purple light, all of those are more energetic than yellow, though not as energetic as UV. However, when you make the room dark enough, purple light is all a highlighter needs to produce its glow effect. Additionally, by filtering out most of the other visible colors, everything else looks darker in comparison. It might be better to think of it not as this light making highlighters brighter in the dark, but making everything else dimmer. To prove my point, here are two blocks of white paint. One is an industrial paint made very specifically to be non-fluorescent, which is rather difficult to find, by the way. The other is Wildfire Optical White, a highly fluorescent white paint. Under normal light, no difference, right? Let's look at it under our DIY phone blacklight. Purple for sure. But you still can't tell which is which, right? If this was actually giving off UV, the fluorescent one should be glowing like crazy. Okay, let's turn on a basic 400 nanometer blacklight. Now there's no question which is which, right? Normally I'd expect the fake blacklight to evoke a little fluorescence out of the one with UV paint on it, but wildfire paints in particular are more discriminating than most. The energy from visible light simply isn't enough to trigger the glow. These need UV to activate. We're about 30 minutes in at this point, so I'll wrap up the video here. We've discussed all the foundational knowledge you need to understand how blacklights work. In my next video, I'll have samples of fluorescent and phosphorescent paints, and we'll see how they look under both a 400 nanometer common blacklight and a 365 nanometer true blacklight.